if you turn to page 253, something that I want you to highlight on this page. So, we talked about this already, but you can use chapter 3 to always find x-intercepts. So wherever the y is, so if you had this as your original graph and there was a y here, and you wanted to find the x-intercepts, you would just replace that y with a 0. Because every place on a graph that has x-intercepts, the y-coordinates are always 0. So if we replace that with a 0, now it's a solve question where you can use quadratic formula, factoring, and again, if you can use factoring, I always think that's the nicest. This one, you could factor out the 2, or you could divide everything by -2. It allows you to factor, gives you 2 points, and we call, on the graph, we call the x-intercepts the zeros of the functions. So what I want you to do right beside here is all of these things mean the same thing. It all depends what we're talking about. Sometimes on a graph we talk about x-intercepts. Sometimes on equation we talk about zeros. Sometimes with a quadratic formula we talk about roots. And if we have a question that we're trying to solve, sometimes we talk about solutions. So all of these words mean the same thing in a quadratic equation. Sometimes you want to find the x-intercepts or the zeros or the roots or the solutions. They all mean the same thing. Some other patterns that are pretty cool with parabolas. So they've got a graph on the top of page 254 here. They have a graph of x squared plus 4x minus 6. And something that's really interesting and really cool with parabolas are called the first differences. And if you start with your vertex and go over one, first you would go up 1, then you go over 1 up 3, then over 1 up 5, then over 1 up 7. And they didn't do the next one, but could you guess? Over 1 up 9. Odd numbers. Which is really cool because I don't know if you knew this, but if you add up odd numbers, consecutive odd numbers, well here, if you add up the first odd number, what do you get? This isn't hard, you get 1. If you add up the first 2 odd numbers, what do you get? 4. What happens if you add the first 3 odd numbers? Have you ever seen this pattern before? You get 9. And if you add up the first 4 odd numbers, this is really cool. What do you get? 16. Do you notice what's happening? They're all perfect squares. You add up odd numbers. If you add up 10 odd numbers, the first 10 odd numbers is going to add up to 100 perfectly. That's crazy. 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus 19. You add up those all the way to 19, you will get 100, which is really cool. So this is going to be if the leading coefficient in front of the x squared here is a 1. You can use this strategy to get the points quickly. Over 1, up 1, over 1, up 3, over 1, up 5. If the leading coefficient is a 2, those will get doubled. It'll be over 1, up 2, over 1, up 6, over 1, up 10, over 1, up 14. If the leading number is a 3, those numbers would get triple. Over 1, up 3, over 1, up 9, over 1, up 15. They get very big, very quick as a result. So I wanted to show you that characteristic, and that sort of gives us another shortcut for graphing. We're slowly developing shortcuts. And if you have that common difference pattern with the odd numbers, then you can tell if something is a parabola or not from a table of values. So what happens here? We went up 1, like here this is up 1. The x values are always going up 1. Do we have the 1, 3, 5, 7, 9 pattern in this one? From 2 to negative 1.5, can you see that you went down negative 3.5? And then here, we go down negative 3.5 again. And then here, you go down negative 3.5 again, and finally down negative 3.5 again. Does that have the 1, 3, 5, 7 pattern? Or any multiple of it? No. This is not quadratic. Do you remember if it's the same? What graph that makes? A linear graph. This is a straight line. It has a slope of negative 3.5. If it's always the same, right, that's over 1 up 2, over 1 up 2, over 1 up 2. That's your slope. Okay? This one we are going up 8.5. Oh my goodness, they made another line. It's going. That one is also not quadratic. If you look at the example they did, their table B is a quadratic. What will always happen with quadratic ones, so these are called first differences. If we look back at our graph that we just had before, right? The first differences were the odd numbers, right? Right beside this, you see that your second differences are always going up by 2? Up by 2, up by 2, up by 2. If your second differences are all the same numbers, is another way to tell that your original function was quadratic. That's a really quick way to find out something's quadratic. You're going to learn in a couple of years when you take calculus, your first differences are like the derivative, your first derivative, and your second differences are like your second derivative. When you get there. Oh, it's so much fun. Okay, questions you can circle from example 2 or just number 6. And we're going to do example 3 right away together.